Hello everyone, my name is Nael. I'm a computational journalist and the creator of Code Like a Journalist, a free online open source course about data analysis and data visualization with TypeScript. Today we're going to talk about the simple data analysis library, a library I created and that I use in all of my projects. To learn how to use the library, we will work with historical daily temperatures in 3 Canadian cities. And our goal will be to answer this question: how fast have temperatures risen in the past decades? To do that, we're going to calculate the average temperature per 30-year period and check for trends. If you have a minute, please add a star to the Simple Data Analysis Library GitHub repo. It's always nice to know that your open source work is appreciated. And also, for this lesson, I'm expecting you to have completed the first steps and the pushing further sections, because I'm not going to explain everything in the code. If you're already comfortable with TypeScript, you will be fine. But if not, it might be a little bit difficult for you to understand at some point. If you want to know when new lessons are available, subscribe to the newsletter, give a star to the GitHub repo, the course GitHub repo, and if you want to reach out, click here to see my contact info. So, the Simple Data Analysis Library is published on GSR. You can check the page here. You also have all of the documentation with all of the methods available with examples. And you could install the library as suggested here and as we did in previous lessons with Dino, add, GSR, blah, blah, blah. But there's a better way. To simplify our lives, I created another library called Setup SDA, which will set up everything that we need and install everything that we need. So let's open VS Code. Let me reopen it. Here we go. And in a new folder somewhere on your computer, you can start by typing Dino add to give all authorizations to write files and install libraries. And you can type in nshiab setup SDA and press enter. And this script will explain to you what it's doing. So first it's checking if you're using Dino or another runtime. You can use it with Bun and Node as well. And it's going to create a bunch of files that you can see in here. So Dino JSON, we know about it. But if you check it, you'll notice that you have two tasks. One to watch and check main with all authorizations by default. Another task to remove some hidden folders, which are some folders that are caching data, and a few more information, including the imports. So some libraries that are included by default when you use Setup SDA, like the journalism library, which is a library I created as well, with a lot of helper functions. Of course, simple data analysis, and observable plot, which is a wonderful library that we're going to use to visualize our data, and it works really well with SDA. You might not have exactly the same versions as I have here, but it should be fine and it will work. So yeah, you see the first steps, your runtime, then it's creating all of the files. Let's have a look. So you can see that you have a node modules. This is where the libraries are being installed. You don't have to worry about it or touch it. You have a folder SDA. This is where we're going to work. A folder for data, in which we're going to put some data, if we have any. Helpers, this is where we're going to create our helpers functions, like we did in previous lessons. Output, this is where you're going to write the data that you want to share with the world or your colleagues. main.ts, which is the file, the TypeScript file in which we're going to code. You can see that for now, there's just a few lines just to get you started. Git ignore, we're going to talk about that in another lesson about Git and GitHub. This is just some files here that should be ignored when you store, when you archive, when you push your code to GitHub. We're going to talk about that. Dino-lock, you don't have to worry about it. It's also part of the libraries that you installed. And finally, the README, which is a markdown file. There will be a lesson about that as well, in which we just explain a few things about the project. So right now it's just how to use a simple data analysis with this setup, but you can update it, and this is what will be shown on your GitHub repository if you push to GitHub. So this is a simple data analysis library installed with setup SDA. It's creating all of this for us, which is very nice. One note about your Dino version. So for simple data analysis to work properly, you need to have at least version 2.1.9 of Dino. To check your version, you can do Dino version in your terminal. Here we go. And you have your Dino version over here. So you see I have a version that is greater than the one required, which is perfect. If you have a lower version, an earlier version, you can do Dino -- upgrade oh, sorry, yeah, I made a mistake. It's not with -- it's just Dino upgrade. Sorry, I should read my own lesson. So Dino upgrade, and it will check if there's a newer version, and it will a latest release, and it will just install it for you. Great. So now the library. So you have simple data analysis, journalism, and observable plot. You have hyperlinks. You can check it. There's documentation. There's examples, but we're going to do to use them as well here. So now that everything is set up, you can use the task Dino task SDA, and this will check main. And so every time we update main and all of its dependencies, the code will be rerun. So let's explain what's going on over here. And maybe I can make this bigger. Here we go. So let's explain what's going on over here. So in main right now, we are importing simple DB from the simple data analysis library, and we are creating a new instance of a simple DB. So this here is creating an in-memory database, and we are putting the reference to it in the variable SDB. Then we are closing the DB at the end of the script. We're not doing much, but that's what the code right now is doing. So when we save main with Control S if you are on PC or Command S on Mac, nothing is happening, but actually it's creating an in-memory database and it's closing it. And we can do our magic over here. So let's start. The first thing that you want to do usually is to create a table. And to do that, you use SDB, new table. You have examples and the documentation in the pop-up. And usually I like to name the tables like the variables. Temperatures, here we go. And so what we did right now is just to create a new table inside our database. If you never worked with databases, but maybe you worked with Excel or Google Sheets, you can think of tables as tabs. So it's like opening a new tab with some data in it in an Excel file or a Google Sheet file. Again, all of the methods have examples. It took me a lot of time. to write all of the examples, but it's worth it. So if you're stuck at any point, you can always use the pop-up and read the documentation. So right now we created a table called named temperatures, but we have not pushed any data in it. So to load data in it, we can use load data. This method here can load local files, but also can fetch data from the web. And we need historical daily temperatures for 3 Canadian cities. I pushed it to GitHub. This is the CSV file. So this is the data. You can see that we have 3 columns: time, T for temperature, and ID, which is the ID of the Canadian city. So to fetch it, it's very easy. We can use load data, and it needs one parameter, which is the URL. As a string, so between quotes. Here we go. So now it's fetching and putting the data inside the table temperatures. And usually I like to see the data, so you can use the method log table. Here we go. And you'll see that we have a nice table in our terminal now with time, T for temperature, and the ID. We have around 131,000 rows. Right now, the table is just showing the first 10. Very nice, right? All of the methods, the table methods, are async, so we need to put await in front of them. Great, so now we have our data. This is how you load data and log it with simple data analysis. Now, we have the IDs here, but it would be better to have the city names, right? The city names are in another CSV file. You can see that we have ID and then city. It would be great to replace the IDs in our temperature table with these names. So to do that, we can create a new table, const cities equal SDB, new table, cities. And again, we're going to load data with the URL. Here it's a URL, could be a local file. By the way, load data is able to load and parse CSV file, JSON files, and Parquet files. If you need other formats, just let me know. I don't know what's going on with GitHub. And we can also log the table. Here we go. So now you see, cities, it's temperature. I don't have the right link. Here we go. And so now you're seeing the first table here, temperatures, and you can see the table cities over here with the 3 IDs and the cities, Vancouver, Toronto, and Montreal. Now, to bring the data in the cities table inside the temperatures table, we need to join the tables. So to join the tables, we can use the method join. So if we want to join the cities into the temperature tables, we are going to do await temperatures, join, and the first parameter here is a simple table, and cities is a simple table. So we can do cities like this. And I'm just going to move our log for temperatures and to remove our cities log. So now here we are fetching the data for the temperatures, we are fetching the data for the cities, and after that we're saying, hey, inside the temperatures table, I want you to join the values from the cities table. And what this method is going to do, it's going to look for a common column between the two tables. And there is a column that is in both tables. It's the ID, right? Then it will match the IDs in the temperatures table with the IDs in the cities table and bring all of the values for the cities. So now you can see that our table temperature has the 3 first columns as before, but there's also an extra column that was in the cities table, which is a city now. And this value here has been added based on the ID because it was the common column between the two tables. It's very convenient. If you know a little bit of SQL, this is called a left join. Let's talk about caching. So right now, every time we are saving our file, we are fetching the data over and over again, and we are hitting GitHub servers. This is not very efficient because the data is not changing, so we could just cache it. One way to cache data with SDA is to use the cache method. Once you created a table, you have access to the cache method. And the cache method takes as an argument an async function. And you can wrap whatever you want in it to cache the results. So like this. And I can make this smaller. So like this. So you see that I just cached all of this code for the temperatures table. And the first time that you're going to run the cache method, it's going to run the code, the provided code, but it will store the results. It will store the results inside SDA-cache. And you can see in there that you have a temperatures file with a very long name, and the data is stored as a Parquet file. Basically, it executed all of this and then cached the result in this file here. Parquet is a very efficient data format. So the data now is stored. The second time that it's going to run this code, it will check if the code that you gave it to, the code that you provided has changed or not. If the code has not changed, instead of running it again, it will just grab the result from the cache. It's very convenient. And it will be, in theory, much faster. If you want to log extra information about the cache, you have an option when creating your simple DB, which is cache verbose, and you can put that to true. So I'm going to do it again. And what I wanted to show you, let me stop this. If you want to clean the cache here, you can do the task dino clean. You see the cache has been removed. So now let's do dino task SDA again to run the code. So we have no cache right now. Let's run the code with verbose. And you can see that in the terminal, cache for temperatures, for the temperatures table, nothing in cache, running and storing in cache. It took 1 second, 43 milliseconds on my computer and with my internet connection to fetch all of the data and to do join. And here's the result. The whole script took 1 second, 45 milliseconds. Let's rerun this. I'm just saving it again. So now it's way faster. Cache for temperatures. Oh yeah, I found something in cache because the code inside the cache method is exactly the same. And the data has been loaded in 15 milliseconds. This is really fast. Running the computation took 1 second, 43 milliseconds last time. You saved 1 second, 28 milliseconds. And now running the whole script took just 31 milliseconds. This is way faster. Here, much of the time is saved on not fetching the data. Retrieving data from the web can be quite slow. It's way faster to retrieve data directly from the cache. But in other lessons and projects, we are also going to use the cache to cache the results of heavy computations that can take several minutes. And instead of rerunning the computations every time you cache them, so you're just grabbing the result if the code inside the cache method has not changed. So this is great, the cache is working. Now we are not hitting GitHub servers anymore, and it's way faster. So let's explore the data now. So to explore data, you can use the method called summarize, which will aggregate your data. So summarize takes an argument as an object, and you can specify the value that you want to summarize. So let's start with time here, this column. And you can also specify categories. So in our case, we have cities, and we will want to compute an average temperature every 30 years per city. So one way of exploring the data is for each city right now. So we can say, hey, time, category, city, let's summarize this data. I can make this a little bit bigger. Here we go. So right now, the table that is being logged, its width is greater than the width of the terminal. So it's wrapping inside the terminal. You can do a right click and toggle size to content width, or you can use the shortcut. So I'm going to use the shortcut to just tell VS Code, hey, do not wrap whatever you're seeing in the terminal. So now we have our summary over here for the time. And so we have a lot of information in here. So first you can see that for each city, we have values. The first thing that is will be a problem is that you can see that the count, the number of temperatures is different. And actually, if I'm not mistaken, we should have around 44,000 days for this period of time. You can see that right now, the minimum date is January 1st, 1900, and the maximum date is 2020, December, the end of December 2020. So in theory, we have 120 years worth of data, and we should have around 44,195 days, but this is not what we're seeing here, which means that we have missing data. We have missing rows of data, especially for Montreal. We have more information, so count unique is important here. You can see that it's the same number for each city, so we don't have duplicate dates. We don't have any null values for the dates. After that, we have a lot of information, some that does not apply to dates. But this is how you can explore your data with summarize. So for the time, yeah, we will have to deal with missing data. Let's check the temperatures. So instead of time for the value, we can say, hey, the value now is T for temperature. Let's reformat the table. Okay, so we have the same problem for count, obviously. It's okay to have a different count for unique because some temperatures are going to repeat the values. But you can see that we have another problem now. For Montreal, we have 8 null values for temperatures, and for Toronto, we have 6 null values for Toronto for temperatures. So we need to clean our data for null values as well. The mean temperature looks okay. Montreal is colder than Toronto, and Toronto is colder than Vancouver. The max temperatures looks good. Then we have a lot of extra information. The variance, the standard deviation, the skew. We don't need all of these information, but by checking with summarize, you can see that, yeah, we have null values. So we need to do a little bit of cleaning. This is very easy to do. So in the cache value, in the cache method, right after our join, we could clean our data right away by doing temperature, remove missing. So if you don't pass any arguments to this method, it will just remove all empty strings, all null values in any rows. It will delete the rows containing any null values or empty strings. You can also specify a specific column. So you have an example, for example, here. But here it's fine. We just want to remove rows with any null values. So you can see that the cache, now we have a message saying nothing in cache because we changed the code inside the cache method, right? So we have to rerun everything inside the cache, which is quite nice. Now the data is cached without any null values, because you can see that now outside of the cache, temperature summarize, null, count null, we don't have any null values anymore. Our data is cleaned. So dates, we checked them, we checked the temperature values. There's nothing else really that we need to check. We can continue. Now, to check climate trends, it's recommended to do 30-year averages. You can check, I'm giving you some academic resources on the course. I will let you check them. Basically, 30-year averages can capture a lot of climate patterns like El Nino, El Niña patterns that are quite important in Canada, for example. So yeah, usually that's what we use. We call them normals as well. So what we want to do now is to bin our data. So if we remove the summarize, what we want to do now is for each row to put it inside a bin that would cover a time frame of 30 years. To do that, we can start by working with the years. It would be great to add a column with just the year. To do that, we can use the add column. So await, temperatures, add column. The first argument is the name of the new column that you want to add. The second parameter argument is the type of the values. So here it will be number. And finally, you need to provide the method with the column definition. This is SQL. Don't worry, you won't have to learn a lot of SQL to use simple data analysis. The reason why we're using SQL is because SDA is actually talking to the database that you have in memory in SQL. That's the language that the database is using. So the methods are always translating what you want to do to SQL. Here, this definition here needs to be the SQL definition of your column. SQL is very simple. You won't need to learn a lot of SQL to use SDA. And anyway, we'll have tons of lessons and projects that will give you everything you need SQL-wise. So to extract the years out of dates, so these here, you can see that they are dates. You can use a function called year, and inside you can pass the name of the column containing the dates. That's it. So pretty simple. And now you can see that we have a column year with the year for each date. Now, what we want to do is to create bins to group the years together and to create 30-year averages. So to do that, we can use the method bins. So as you can see, there's a lot of methods available to do pretty much anything you need to do when doing data analysis. If there's a method that is missing, just send me a message and I'll be happy to add it if relevant. So the first argument for the bins method is the column to use to do the binding. So in our case here, you can see that we want to bin the years. Then it's the interval. So the interval of the bins. So here it's a 30 because we want to do 30 year averages. And finally, it's the name of the new column that will contain the bins. Here we go. And you can see that now we have our bins in the column bins. And you can see that the first bin here, well, for this value here, is 30 year of data. It works. So we have the categories for each row. Just to make sure, we can use a method called, we can log the result, console log, await temperatures, get Unix bins. So this method here will return all of the unique values inside the provided column, so here bins, and console log will just log the result. So you can use that sometimes to check, it's bin. Here we go. And so you can see the values that we have here. They look pretty good. Everything makes sense here. And so finally, we need to summarize and filter our data. So we can use summarize again, but this time with different values. So let's call summarize and open an object for the options. So the values will be T, the temperatures, right? Because we want to create a 30-year average of temperatures. The categories will have two categories now. We want the 30-year averages per city, but also per bin, right? We want to do that by bin to have our 30-year averages. For the summaries, which is an option that we haven't used so far, when you don't provide summaries, it will compute everything that is possible to compute, but you can also specify just what you need. So in our case here, we want the mean, the average, and we want the count as well. How many rows have been aggregated together to compute the mean? Because this will help us deal with missing data. And we can also round the values. Let's keep only two decimals. Here we go. That's the result. So we have the average temperature for 900 to 1929 for Montreal. You can see the mean and you can see the count over here. SDA is telling us that there's 15 rows in total in this table, but it's just logging the first 10. So let's update that to see all of the rows. You can pass an option number rows to log table, and let's put 15, so we'll see all of the rows. Here we go. So now we have a great view of our 30-year averages, and we can see a few problems right away. For example, this here, Montreal, you can see that there's a lot of missing data for this period, 1990 to 2019 for Montreal. Looks like there's a lot of missing temperatures. There's also a lot of missing temperatures for 2020, 2049, but this is expected, right? We don't have data for the future. Same for Toronto and same for Vancouver. So in our analysis, we probably need to add a threshold to say, hey, if you need at least X% of data if you don't have X% of data, we are going to exclude this time frame. So to do that, we can use filter. And we can filter the data right after the summary. So temperatures oops, temperatures, filter. Again, you have documentation and examples. Here we go. You're not forced to use backticks when you're creating SQL expressions, because filter will need an SQL expression as well. I just like to use backticks because it makes my code easier to read. When it's backticks, I know that it's SQL, and also backticks will allow us to do to do variable injection inside the strings, which is very convenient, and we're going to do that a lot later on. So if we want to keep only rows with at least 90% of expected data, we can say, hey, I want count to be greater or equal to 9,861 days. So this here would be 90% of days in a 30-year period. So now if we save, and you see count is the name of the column count here. So we're just using this very simple expression. SQL is very simple to filter out the data. And so you can see now we don't have the problematic average for Montreal, and we don't have any more 2049 bins. Now we can check for trends. But first, there's something that is a little bit annoying. So the bins right now, they are text. If we want to check for trends, for how temperature have risen over the decades, it would be better to have dates or numbers to help us calculate trends. Because right now this is text, this is a number, but you cannot really calculate trends based on text. So what we could do here is maybe we could extract the starting year of each bin and put it inside a new column. And so then we'll have a number. So we can use the split extract method. So the split extract will split a string into a list, an array of strings, and you can specify which one you want with the index. So the column that we want to split is bin. The separator here that we can use is the dash. So the data, the string here will be split in two based on the dash, which is a separator here. And finally, the index. So the index in here would be 0 because we want the start date. And finally, the new column. So we can call that start year. Here we go. So you see that the string has been split on the dash, and the first element, so this here, has been put inside the new column, start here. We can trim the new column here, start year, and we can pass as an option the character that we want to trim. So here it's an opening square bracket. Beautiful, so we are left with just the start here, but this is still text. We need to convert it to a number. So we can say temperatures, convert, and the argument is an object with the name of the column. So here it's start year, and what we want this column to be converted to. So in our case, we want number. Here we go. So now we have extracted the start year of the bin and put it inside a new column, start year, with the method split extract, trim to clean, and convert to a number. And now we can use start year with mean to check for trends. Let's visualize our data. To check for trends, of course, you can visualize data for example, with SDA, you have a lot of methods, including methods to visualize data directly in your terminal, like log.chart. The first argument is the x value. So in our case here, it would be start here. The second one is the y value. So it would be the mean. And you can pass an option for small multiples to create several small charts depending on the values of a column. So in our case here, it would be great to have small multiples based on the city. And you can see in our terminal, we now have dot charts, one per city with the average temperature. You can see that the temperature clearly increased in Montreal. This is the 30-year averages. Same thing with Toronto, and same thing for Vancouver. So this is a very simple way to quickly visualize your data with SDA directly in your terminal. But there's another way. You can use observable plot, which is a wonderful data visualization library. There's a full lesson about it, and I'm going to record a video for this one as well. I'm not going to explain the syntax too much right now. I'm just going to actually run it. So the way it works is that you create a function chart, or it could be named anything else. This function will draw a plot chart. We have a lot of options here. I will explain that in another lesson. And after that, you call the method write chart on the table that you want to visualize. You pass your function, your drawing function, and you pass a file path with PNG, JPEG, or SVG if you want vectors. And this is where your chart will be saved. So this code here, you can see, is creating a new chart temperatures inside the output folder. And this is this is the chart that Plot has created. And we can clearly see, again, increasing 30-year averages for the temperature in these 3 Canadian cities. So Plot, wonderful library. We're going to use it extensively. And yeah, you can open images with VS Code, which is very nice. If we change the code creating the chart, the code is going to be rerun and the chart will be updated automatically, which is very nice. Now, visualizations are great, but when you are checking, but they could be quite subjective, right? Is it really increasing, or is it just you that is finding it this way? So when checking for trends, you can also use statistical indicators, like, for example, correlations and linear regressions. There's a lesson called Math for Journalists. If you are curious, you can check. Check it. It's an interactive notebook that I created for my colleagues to explain all kinds of mathematical concepts with interactive examples. So check it out. Could be very, very useful. And if anything is missing, just let me know, and I'll update it. So instead of visualizations, you can also use correlations, for example. So let's do that. It's very easy to do with a simple data analysis. We have the methods available directly. So you can do a weight, temperature, correlations, and you need to pass a few options. So the X values here would be the start year, and the Y values would be the mean. And again, you have the categories options to calculate the correlations for each city. And you can see that the correlation between the years and the average temperature is positive and very close to 1, which means there's clearly a strong relationship between the two variables. When one goes up, so when the year are increasing, the temperature is increasing too. There's a strong relationship between the two. Another way to check for relationships is by using linear regressions. So you can just switch correlations to linear regressions. It's a different method, but it's using the same options. And if we save, maybe we can add another option called decimals to round the values. Here we go. And so now you can see we have the linear regressions information for each city. And you can see that the R squared is very close to 1, which means as well there's a very strong relationship, a linear relationship between the years and the average temperature. And you also have an extra information which is very nice with linear regression. It's the slope. Here, this means that on average, the temperature increased by 0.02, sorry, on average, the temperature increased by 0.02 Celsius degrees every year. So these 3 Canadian cities definitely warmed up. We have checked for trends. Writing data. So usually when you have an analysis, you want to write a file and maybe share it with your colleagues, or maybe you want to use it in a web project. So to do that, you need to write your data, and we can do that fairly easily. So I think, yeah, in the example here, I'm just writing the whole data instead of an aggregated version of it. So not the linear regressions, just the, if we save, so let's say that we would like to save this data here inside a file. So again, you can call your table and use the method write data. And you can specify the path for the file that you want. So here, let's say that we would like to put it inside SDA and then output as usual, temperature.csv. And now you'll see that you have a CSV file, which is a text file with the data separated by commas that has been written. Very easy. If you want, you can also write it as a JSON file. Here we go. So you can see it's an array of objects. And if you want, you can do Parquet, which is another very efficient. So you cannot visualize Parquet data inside VS Code, but it's a very efficient file format that works great with simple data analysis. And that's it for this lesson. We've done a lot of things. It's been quite an adventure, but I hope that you see how simple data analysis can make can help you out with your data analysis. You have a lot of methods available to do all kinds of computations. You have the documentation, examples. It's clear. It's quite easy to understand. Everything is very explicit. Yeah, I use it every day. Here we used tabular data inside the tables, but you can also work with tabular, with geospatial data, to work with points, polygons, boundaries, and this is what we're going to do. We are also going to create maps in the next lesson. If you want to know when new lessons are available, subscribe to the newsletter, add a start to the GitHub repo, and see you for the next lesson.